Director Secretary, Dr. Sumitha Nathan. I will request Sumitha to take the charge. Sumitha?
Hello, can you hear me?
Yeah, I can. Please go ahead.
Hello, everyone, and a warm welcome this evening. And I welcome you all for a guest lecture on transportation systems, resilience, models, and algorithms, organized by Operation Research Society of India, Ahmedabad chapter, and Department of Mathematics at Gujarat University. So the speaker for this evening is Elise Miller-Hooks, and she is a professor and a Hazel chair at George Mason University. So I would like to give a brief introduction of the guest today.
Would you like me to do that?
Can I share the screen, ma'am?
Oh, yeah, I'll stop sharing. I'm no longer sharing, so I think you need permission.
Yes, Sunita, please go ahead.
Dr. Elise Miller-Hooks, she holds the bill and just not able to see it properly. 1 minute.
Would you like if
you can read it? No problem.
I could do it really quickly if you like.
No, ma'am, I'll do it. So,
okay.
Dr. Elise Miller-Hooks, she holds the Bill and Eleanor Hazel Endowed Chair in Infrastructure Engineering in the Sid and Reva Dewberry Department of Civil, Environmental and Infrastructure Engineering at George Mason University. Dr. Miller-Hooks, she has served as a Program Director of the National Science Foundation Civil Infrastructure Systems Program in the Civil, Mechanical and Manufacturing Innovation. And she has also led as a Program Officer for the Critical Resilient Interdependent Infrastructure Systems and Processes. And she has also been a Cognizant Program Officer on CMMI's Smart and Connected Communities, that is Smart Cities Initiative. She has served on the faculties of the University of Maryland, Pennsylvania State University and Duke University. She has received her PhD and MS in Civil Engineering from the University of Texas, Austin, and her Bachelor's in Science in Civil Engineering from Lafayette College. She has an expertise in disaster planning and response, and she has also received many awards, including some national awards related to her PhD dissertation as well as other dissertations and on her ongoing research. And she has authored approximately 150 articles and reports. And she has also been have done presentations over 230 conference presentations, and also has invited or keynote lectures. She serves on the editorial board of the journals like Transportation Science, Operations Research, and Journal of Intelligent Transportation Systems and Transportation Research. She is the chair of the TRB Transportation Network Modeling Committee. She is also founding co-chair of the TRB Task Force on Emergency Evacuation. She has also been the past president of the INFORMS Transportation Science and Logistics Society and the Women in ORR MS Forum. So, a warm welcome to you, ma'am, and over to you.
Great. Thank you very much. Let me go ahead and share my screen now.
Yeah, I'll just stop share.
Okay. Well, thank you. Thank you so much for having me at this for this lecture, and I'm really pleased to get to meet you all. I hope that we'll have a chance for a few minutes afterwards just to get to talk a little bit, so I can get to know you all as well. So I'll be talking about transportation systems resilience and models and algorithms for this throughout this talk, and try to share with you some thoughts after doing work in this area for probably about 16 or 17 years now.
Recording in progress.
So infrastructure lifelines are crucial for societal function, and we all know this. Transportation systems in particular are the backbone of modern societies, providing mobility for people and goods, and connecting businesses and supporting lifelines and providing access to jobs and so on. And they're also interdependent with other lifelines. In the US and in many other countries, these infrastructures are aging, they're operating at their capacity limits, they're often located in vulnerable locations because we love to live in those vulnerable locations, and they're increasingly dependent on cyber, so that makes them vulnerable to intrusion. So it's really important to maintain them in a way that they can be resilient. When we talk about resilience, it's become a really big buzzword, so it's used broadly. But when I talk about resilience, I think of it as having two key components: the inherent coping capacity of that system and the ability of that system to adapt when something goes off track and something goes a little wrong. And I think of resilience in terms of actions we can take as well. And so we have this idea of this action framework where there are actions you can take along that disaster cycle. So there are actions we can take ahead of time that are mitigative, that help to prevent something from having a bigger effect. And then there are those that are preparedness related, where you take an action that has no implications in general, unless you have to use it. So it's preparing for the recovery and then the recovery. And so we can have different types of metrics that come from different types of actions that we put together. If they're all taken ahead of time, we'll consider that one type of metric. If they're all in the post-event phase, they might be something like flexibility. You see that in business. Resilience can also be considered in terms of point versus period resilience. So we might look at the resilience of a system at a particular point in time, or we look at it over the whole recovery from when the event occurs and until we get back to a level of service that we feel comfortable with. I'm going to focus primarily on point resilience through this talk, but I've always felt that these things are sort of two different sides of the same coin. So actions contribute to both the point and the period metrics. More traditional hazards that we'll consider are natural hazards, malicious attack, which could include a cyber attack, and technical and accidental kinds of failures. We see failures becoming a bigger issue, and these technical failures due to the role of computers in the operations of our infrastructure. So bugs in code can cause a major disaster. You'll see that I take a multi-hazard approach in almost everything that I'll talk about. And that is because I believe very strongly that if you take an action for one hazard, it's likely that it could be detrimental under another hazard or a different event of the same hazard. So it's really important to think about how to hedge against the different things that can occur, and we then have multiple scenarios that we're always thinking about simultaneously. There's also the issue of compound hazards, and never has this been clearer since COVID, where almost anything that happens on top of COVID, we just think, oh my God, how can we deal with yet another thing? So they might occur at the same time, or one might follow or induce another. So my group has looked at resilience from a lot of different perspectives and a lot of different applications. And we're continuing on to even more. Right now I have a project in the Arctic, and we're looking at resilience for the Arctic people. So that's people who are living in very extreme conditions. I'm going to talk today about a few of these and try to give a bigger picture of this. How do we quantify resilience for different systems, and what are the differences in doing that across them? How does it change our way of mathematically modeling them, and what does that infer about the solution techniques we use? So here I'm just giving you a sort of an overview of where I'm going. I want to talk about that mathematical form in each application and the implications for needed data and solution. And then questions that have more to do with interpreting resilience. So for every different application, we'll need to think about performance. We'll need to think about the continuance of, sort of like business continuities, but the continuance of that operation in terms of that performance metric. And we'll ask, whose perspective are we taking? What if we're in a competitive environment? Should we look at the technical system or look at the system user? What if we have diverse users? What if we have multiple infrastructures? So that, I think, is a really important question to ask that I think is rarely considered, at least explicitly. Resilience sometimes can have a value greater than 1. So what does that mean? I'm going to use an agnostic metric that has a top value of 1, meaning I'm going to use a baseline of before an event or without an event, and then compare how well do I do during events compared to that baseline. And so in the best case, I should do as well as I normally would do. But sometimes we take adaptations that lead to performance that looks better in terms of performance metrics. So for example, in my hospital work, when we think about resilience, we have to consider the fact that in a disaster event, we might allow different standards of care. And if we allow different standards of care, we might process patients faster. So the throughput through the hospital might be greater. The wait times for the patients might be lower. It looks better. It looks like we have this amazingly resilient system. However, we've taken adaptations that lower the standards. And then questions about baselines. What do we use in a baseline? Should we look at ordinary disruptions? Should we look at perfect conditions? What about system congestion? What about the different users? So I'm going to start here with the very first thing that we did. This is work from about 2005, where my student and I were really just thinking about networks and how in the network theory, the types of things that we could assess quantitatively were not accounting for actions you could take post-event. And so we were thinking of an example where you have a computing system, so you have a communication system, and it has a single point of failure, a router. And that would look terrible. It'd be terrible to have a system that has a single point of failure that takes the entire thing out. However, if you could account for the fact that you could have a router sitting in a box in a closet, you can then restore your service quickly if you had someone who knew how to implement it, then maybe that system is not so bad. And so how do we mathematically account for that adaptation? And when we first started this word resilience was really not around. There was a few papers on it, but not a lot. And we weren't sure what to call it. We were calling it flexibility. And then we were talking to the social scientists who said, maybe that's resilience. And so that's where we started. And when we started it, we wanted to mathematically model it. And this is the mathematical model. It's a stochastic program. You see the C are our scenarios. And what we were doing is the different scenarios could come from different hazards. And we were trying to assess how resilient is that system, given that it's going to have reactions once something happens. We're going to take action once something happens. We were not trying to optimize anything, but we ended up optimizing. So we end up optimizing the resilience actions that one would take in response to the scenarios. So I'm not going to go through all the notation. I'm going to have a lot of notation here, but I'm going to talk in general about the types of formulations. What we realized is we could decompose this problem into independent, deterministic, but NP-hard problems. And we gave an exact solution approach for solving this. We could take an expectation over all of them, over all the scenarios, the solutions from the different independence programs, and then we could have a measure of resilience. So here we just look at it as these independent problems for each scenario. I'm calling it a one-stage program. We used to call it a two-stage stochastic program with no first stage because we didn't know what to call it. All right, so we took that concept, we applied it to originally to rail and then to a port. We used the Port of Swinoujscie in Poland because we had a project that worked with these folks, and they were wonderful at sharing data and understanding of how the port operates. We had a model of the port where we took some of the physical elements and we modeled them in a way that maybe is a little not different than the standard. So, for example, a gantry crane would be modeled as a link, and the gantry crane picking something up and moving it would be the travel time on that link. So it was a little bit abstracted. So we have this model of the network. We have the base flows through that port, and then we had 5 classes of events that might occur, from earthquake and flooding to targeted malicious attack. And from each of these, we would generate scenarios. We generated over 10,000 scenarios and gave ourselves a budget. So we're basically saying that resilience, we said that something is resilient, or we can compute its resilience based on its performance in a period of time that says, I'm going to give myself a time period by which all my actions have to be taken. If I'm still taking it a month later or weeks later or years later, I'm not going to count that as resilient. It's too long. It should be quick. So the actions need to be quick to say, okay, yes, you can take actions, but if they're not quick enough, I'm not going to count it as contributing to my, the health of my system. And likewise, we give a budget. That budget is really about just effort that we put in. So how many crews do we have doing something? So we estimate resilience on the right-hand side here for this port, and by using that baseline, we can get a percentage of throughput that we get through that port under those different budgets for taking action. And on the left-hand side, we call this point resilience. You see 10,000 points on each of these lines. And one of the interesting things you'll see is that if we have no budget, that means we can take no adaptive action, only have the coping capacity of the system. We'll have cases where there's zero throughput. As we increase our budget, that worst case gets better and better. So the range on the behavior is much smaller and performs better. So the next thing we did is we said, wow, well, we know that we have this sort of resilience toolbox of actions we can take after the fact. And those actions can be from different entities. So we could look at, with that particular case, we were able to look at which stevedoring companies were performing better and how they might back each other up and things like this. But if we know we're going to take these actions, we can prepare for those actions. We can do something to put things in place and make other actions available. We can also take other preparedness actions like mitigative actions that would maybe increase the capacity so that we have more capacity to cope with what might come our way. So we added in this preparedness piece. So we have beta is now our preparedness actions. We have a budget for taking the preparedness action. So actually, if we have one budget, we could decide how much to put in before versus how much to use after. When to use your resources. We could have added capacity from taking that action or not. It depends on what the action is. So, for example, you put some kind of concrete barriers into storage where you can deploy them. That would be an action that was a preparedness action, but it would add nothing unless the event occurred. We could have a lower cost for taking a recovery action if we took a preparedness action, if they're connected, and the implementation time for that recovery action might be faster if we already took a preparedness action to support it. By adding just these exact things in the purple lines into this model, we end up with a two-stage stochastic program now. So we cannot decompose the problem by the scenarios any longer because we have these preparedness actions that have to be identical for them. And so we model it that way. We end up using an integer L-shaped decomposition method to solve this. So I just show in this picture that now they're connected. We applied this to an airport and a number of other applications. And in this airport application, we're looking at the operations of runways and taxiways. And our objective is now about the number of takeoffs and landings of small and large aircraft. We account for all kinds of operational details, like does the small aircraft take off after a large one, or a large one takes off after a little one? They have different headways that are required between them, depending on that ordering. The configuration of the runways and how they're used. We have weather conditions and visibility. We look at the taxiways and directions of flows on the taxiways and how much capacity we can get out of them. Minimum operating strip length for military applications as well, just because it's fun mathematically, we put that in. And a number of other things that have to do with the repairs. And we embed that in a decision support framework. Then we'll have our two-stage stochastic program that's a little more complicated than the one I showed you on the previous slide, because it includes all those operational considerations. And then we have that integer L-shaped solution methodology, and we can, from there, get resilience estimates. And you'll see here, we generate scenarios now with the meteorological conditions, because those conditions affect what happens in the event, but also what actions you can take and how long they take to implement. We considered 3 different types of disaster events, from extreme climatic events to operational events and intentional malicious acts, and the types of damage that can happen to the runways and taxiways as a result of them. We include weather-dependent multipliers that account for how long it might take to implement some action. And we also have that some disaster events cannot occur under certain weather events. You cannot have certain kinds of damage to the runway from heat if it's in the middle of winter and we're under ice. And we ended up with a number of different solution or outputs from running this that are really interesting. I just want to focus now on the resilience and difference curves. Here, we're trading off the budget and that time. So let's say we said, resilience, this thing is resilient if within a few hours, I'm able to, get so much throughput. And so how much throughput compared to the original do I get with that number of hours if I have no budget, if I have some budget, if I have a lot of budget, and vice versa. So we can have these contours of resilience. We can also break down each of these by the extreme event. So this particular, so the class that the scenarios are being generated from. So this particular case, we have that the extreme climatic events are fair, the airport fares worse under that than it does under operational events. And then we can have different types of actions we can take. We can turn on and off the variables to estimate coping capacity with and without internal action, teams who can take action and be at the ready, and all these kinds of things. We also thought that in our work and in many works that have come out that people are not accounting for maintenance or that the facilities deteriorate and that they're all in different conditions. Like, we don't all have perfect infrastructure. It's almost never perfect in the second that, time starts to go on, it's already imperfect, it's already deteriorating. So we're taking maintenance actions at the same time that are improving them. So we don't know exactly, what state things are in. And we want to account for that in understanding resilience. So normally we would consider everything to be pristine and it's moving along in this straight line here. And then we have an event and then we have a degradation in the performance of that system that then comes back slowly over time. And we were measuring either the duration of time it takes to come back to a certain level or the pre-event level, or we're taking a point in time and asking how resilient are we by this point. And on the right-hand side, I'm suggesting here that there are a number of different components, they're all in different states, and they're being maintained at different rates. And the system, if you think about its performance, is going up and down as conditions change, as we have some deterioration and we take action. And the point at which the event occurs will affect how well the system handles it. So if you're in a deteriorated state, you're more likely to have the road, for example, wash away or to erode than you would if everything were in pristine condition. So you might end up in a worse situation depending on what the timing of the event was compared to the deteriorated state of our elements. And then it may take longer or shorter to recover. And so as a result, our resilience should not be just one point or one number. It's actually a series of numbers that are changing over time. We looked at other systems where people are involved and people can make decisions and we can't force them to do things all the time. And we can't leave them on the side of the road. If we were, in rail, we might just say, just get this map through and leave the rest behind. You can't do that when the people are involved, right? So here we looked at something we're calling travel time resilience for roadways. We have here a bi-level program now where at the top level, we're dealing with the same kind of things in resilience. The only thing is here we use a 3-stage stochastic program instead of 2 because now we're separating the mitigation from the preparedness and the response. So if, initially we know lots of different things can happen, then in time, we might be just a few days out from a disaster event. Like here, we knew that Hurricane Ida that just came through was coming. Didn't know exactly where it was going to hit. We didn't know the actual impact that was going to be, incurred. But we can start to get ready for Hurricane Ida in particular. So we'll have preparedness actions that we might implement, and then we have the actual thing realized and all the different ways that it might be realized. And then we will then assess for each one of these endpoints. We'll need to assess how does the system do. And so here, our lower level is partial user equilibrium. So user equilibrium is often used to model traffic and to assess delays that come from events that happen in there or congestion. And the partial user equilibrium, the partial part is just saying that we only allow those to switch paths who have been directly impacted. So now we have this bi-level program, and a 3-stage stochastic program. At the top level, once things are realized, we see the performance of the system and how people respond to it, given the things that we've done to help them. And we get feedback. And ultimately, we'll have a solution that we get at a Stackelberg equilibrium between the two levels. We reduce the problem to a single level program by showing that the KKT conditions, the Koresh-Kentucker conditions, are necessary and sufficient for the PUE. And then we use progressive hedging to solve this. In addition to some of the things I've just shown you, we did a number of other applications. And then we said, oh my gosh, we've been thinking about transportation systems all alone, like they operate in isolation. But actually, they're interdependent with other infrastructure lifelines. And so we wanted to think a little bit more about that. So we looked at traffic and power networks and the power distribution system. In particular, we took a roadway and we said, okay, here are the feeders from a substation of the power grid. And we connected these. So we have these two interdependent lifelines. And we modeled them as a 2-stage stochastic program at the top level. And again, the user equilibrium, sort of response of the users at the lower level. So again, in a bi-level structure. And here in the 2-stage stochastic program at the top level, we're modeling both infrastructures and connectivity between them. So there's these state variables that have to match between the two systems. If one is in one state, the other one has to match, at the same time. And so we have this connectivity between the two mathematically. We're looking at traffic signals being at these nodes, and that when power goes down, we'll have a longer time to get through those intersections, creating delays. And then we can take different actions. What's interesting here is that now for the first time, we're thinking, well, whose resilience? Are we looking at the transportation system's resilience, or are we looking at the power system's resilience? And what if I only look at the transportation system's resilience? How much unmet power demand is there? And if I flipped it, how would that turn out? And so it just opened some questions that I thought were really interesting. We also looked at transit systems. And here, instead of considering it as a technical system, we said, let's think about this from the user perspective. Different users are going to have different experiences, even in ordinary circumstances, with their transit systems. Some may be mobility impaired, while others may be really savvy with ride-hailing apps and so on. So when they experience this system, they're going to see it differently. So one might say it's resilient, while another might not. So when we incorporate that user perspective, we now induce a coupling of technical systems, because the people of different populations may use the communication systems when something happens. And if they do that now, I've got interdependency between my transit system and my communication system, even though I wasn't trying to look at it in an interdependent system to start with. A couple other things. I have interacting populations, so I can't look at them separately. And I have baselines that are unclear, because different users will have different experiences. And so whose baseline do I use? And there's uncertainty normally. So we need to think about the system from all these different perspectives. We used a technique developed on fault tree, an extension of fault trees, where we're using a multi-value decision diagram instead of a binary decision diagram, and multi-valued logic functions, and ultimately can efficiently assess these top nodes, which gives us the level of service for the different populations, and we can look at solutions from that. I'm not going to go into all that because I know I'm going to run out of time soon. Let me see what time it is. Okay, so a next thing that I wanted to share with you is taking this a step further. So as a civil engineer, we're doing a lot of operations research, but in civil engineering. In our undergraduate studies in civil engineering, we never talk about people. We only talk about the engineered system. But we don't build civil society for ourselves or for the system. We build it for people. So here, we can think about these buildings as being built to, support us and sustain our lives. And they depend on, the functionality of these buildings depend on these interdependent infrastructure lifelines. So we can model these interdependencies, and then this system of buildings that supports the activities of people as being dependent on those interdependent lifelines. And so here, instead of taking the resilience of one of these systems or coupled systems or triple systems, we're really going to look at the resilience of the societal function given its reliance on this infrastructure. Here we looked at the health system at the top level and what we call WET, the water, energy, and transportation triple. And so these are interdependent and they're supporting the hospitals. And in particular, we're looking at hospitals. So we model this as a 3-stage stochastic program. Our objective now, the performance function we will use in assessing the value, assessing resilience, is a function of unmet demand and wait times and access and transfer times. So quite different than in rail system where we're looking at throughput, for example, or flows. We use a meta model for assessing wait time that we generated or developed from individual hospital models that we developed in great detail. So we worked with Johns Hopkins and their hospital systems in the area where we live and developed very, very sophisticated hospital models. With those hospital models, we were able to develop this wait time meta model that we then embed in the objective function for that 3-stage stochastic program. One of the interesting things here is that the stages of this program are quite different than what I showed you earlier, where we had the mitigation, preparedness, and response. Instead, here we have the first, pre-event, then the event occurs, then we take actions. Like we might have power, a power system that's backing up our system. And so that one, though, might run out of fuel, or there might be some uncertainty when we can refuel the generators. And so we get to another point in time where conditions have changed. And so now, even in the response, we have different things occurring, and they may be worse even over time. We look at that evolution over the multiple stages, and we also look at the lifeline state variables I mentioned before, in incorporating that interdependencies between the different technical systems, the lifelines. So this is modeled as a 3-stage stochastic program. We applied it to Johns Hopkins hospital system in our area. There are 5 hospitals, and I won't go into those details, but I think it's interesting to think about, like, how do you get those hospitals up and running, keep them up and running, and how resilient are they, given that we need to take actions on power or water or transportation. We can't keep a hospital open if there's no water, if there's not enough water supply, or there's not enough pressure in the water to put out a fire, for example. You would have to close the hospital here. Likewise, if it has no power and we lose the backup generator capability, we're going to have to close down that hospital. So we need to keep those lifelines up. We also very recently worked on a cyber attack on hospitals. So using that hospital model that I was mentioning to you, that's very sophisticated, all the details, we're using it, we've extended it for COVID, but we've also extended it now to incorporate cyber attacks, and we're looking at ransomware as well. A totally different perspective now. Here we have a global port network that we're looking at. And the idea that I was thinking about when we started looking at this was that I was saying that a port, we look at port resilience. And I was talking with the port of in Singapore, and there they have a lot of money. And they said, oh, well, we're just going to make it the most, as they build their new port, it's just going to be the most resilient port ever. We can take every action we might want to take now, and there's no need to worry. They were mostly worried about cyber attack. And I said, well, that might be true, but you're part of a larger system. And as part of that larger system, your port that's connected to you, that's part of the routes of major carriers will, if one of those goes down, you're going to be affected. So if something happens in one port, it percolates across the globe. And that's all that this is showing, that you'll have backups that can continue to back up. Okay, so we said, okay, let's look at the single ports, a single port perspective for a moment. So we'll take actions at an upper level again. So we have this bi-level model, where at the top level, we're looking at the expected port throughput. If we take some actions, we might make it be more resilient, so there'll be better throughput when an event occurs. And at the lower level, we have a liner shipping problem. So it's like a global market clearing problem. And everyone shares that market. from the single port's perspective, I can solve this problem and I can get what's best for them to do. And here, this is just showing the reduction to a single level problem. The thing is that port cannot operate by itself because it's part of that global network, right? So we actually have to look at all of the different ports at the same time. So here, when we put them all together and recognize that they all share that lower level problem, that market clearing problem, that line of shipping problem, they are connected at their lower levels. And so I have them all trying to do the best for themselves, but they have this market that's at the lower level. And so we end up with an equilibrium problem with equilibrium constraints, and it's stochastic. And so it's a multiplayer problem. And so they're all trying to do what's best for them. And what I'm suggesting is what's best for each of them may actually be not to just invest in themselves, but maybe to invest in each other. And an equilibrium solution, so with the single user problem, we are looking for a Stackelberg equilibrium, and we have that here as well. But now across players, we're looking at no port can unilaterally change its investment strategy and improve its expected throughput over the scenarios, or some other measures that we look at. We use a diagonalization approach to solve this. And here, if we look at this problem on the right, so here's our original problem. We have ships moving around in these ports. If nobody invests at all, then this just reduces to that lower level market clearing problem. If we only invest in ourselves, every port only puts money in themselves, then we have a restricted game. If they can invest in each other, then we have an unrestricted game. And what if only some of the ports play and some don't? Some only invest in themselves, some are willing to invest outside. We have a semi-restricted game. And then finally, what was in the literature primarily was just, I have a single pot of money, how do I spend it? And so it's a centralized approach. That just doesn't happen. And then we have to ask, whose resilience? Is it the system's resilience, the OD demand served kind of thing, the origin destination demand served? Or is it the port's resilience? So it's the port's profits? Or is it the shippers? The shippers care about costs. So how do we measure resilience of this system? And we have a number of different metrics we also use from this, considering the stochasticity in this problem. That I don't want to go into the details here just because there's not enough time. Taking the port a little further, in very recent work, I've been working with the Port of Singapore, as I mentioned them a second ago, and folks at the National University of Singapore. And at the National University of Singapore, they have developed a digital port twin, which is pretty exciting. And it's a big undertaking. So we could model the digital port, the actual port with a whole lot of math. This is the one from the airport. I'm just saying it could look something like this, where you get all the operations in there. But instead, we're going to replace this mathematical model with a simulation. So these are very complicated. We're going to use the digital port twin in place of this mathematical model. Not entirely, we still need some mathematical modeling, but because we still have to understand resilience, but the little details of it will come from the simulation. Here, we're interested in birth on arrival. So that's how we're going to measure resilience. So when a vessel comes in, how fast is it birthed? And if it doesn't birth on arrival, like within a certain amount of time, then we don't consider it as having birthed on arrival. We have partial shutdown scenarios due to power loss. And we are thinking about in a real-time framework, you would have the simulation and the actual system feeding back and forth to each other. So you can keep it up to date. So this is really interesting. It's a high fidelity kind of model because it has so many details of all the operations. And it also can account for ordinary operational uncertainties, which we normally can't do in these models, and the uncertainty in the performance of the recovery actions, which I've always wanted to do and never was able to do that mathematically. We have different scenarios that have to do with power shortages and different actions that we might take in response that have to do with alternative ways that will give the key cranes and I'm forgetting the word, the AGVs, the automated guided vehicles, how much power each of them will get when we have limited power. We can assess the resilience of this. But what I wanted to share with you is this other addition that I thought was kind of cool. So my colleagues are experts in simulation optimization, and they have an approach called the optimal computing budget allocation, which essentially is saying, when we have a situation with these large simulations, and we have to run them fast, and we have to run many of them, we can't run as much as we would like to run. So if we efficiently decide on which scenarios to run more of, we can get better estimates. And, we can't know this because we're trying to assess a function, and we don't know exactly, we wouldn't just be able to do this by winging it. So they have this approach mathematically that's seeking to maximize the probability of correct selection. And so here what you can see is by implementing this OCBA approach for the simulation and deciding which replications to make for the different scenarios, if you used an equal allocation across the scenarios, you would have this probability of correct selection from 0.65 to 0.78. With OCBA, it's as high as 0.92. So by using the same amount of simulation budget, we can actually have much, much better estimates of the real actions that we take. So it's probably correctly selecting the action to take when an event occurs. And we can also look at the speed up of the OCBA over the equal allocation if we were to use a preset number, or we want to get to a value and say how many simulation runs does it take to get to that. Last, I want to leave you with some thoughts about the future. So we are now working in an automated and interconnected world, and there's real-time information and monitoring and control, and there's sensors that are ubiquitous in many systems. We don't have to guess at all the different scenarios that might arise in the future. We might actually be able to see them happening or see details of them as they are about to happen. So we may be able to exploit some of that information. And the roles of humans are changing in these systems. And I think that's a really important point as things become more automated. They're increasingly decentralized. There are new and personalized and responsive services. And they also can create new hazards, so now we put cyber into everything and we realize, wow, we've now made opportunities for more failures. And the actions that we can take to respond may be different. In fact, our ability to respond may be different. So I'm thinking about my children, if they're older now and they're driving, but if we had automated cars, or maybe in 10 years from now when there's more automated cars, more and more people won't know how to drive like with intuition. So they might know how to do it, but they won't have practice doing it. They won't be able to, they'll have to think to do it. And that will change the ability of us, for us to respond. We see that with aircraft as well, as pilots are increasingly relying on automation functions. And also in hospitals, even doctors are relying on some of these computer kinds of backups, so that there are many things we don't do by hand anymore. And so when you have to do it to be at the ready when those things fail, it's a little bit harder to adapt. So there's changes that are coming, and I just wanted to note that this is a direction that I think will require a lot of attention. Agents can also operate in adverse conditions. That's kind of neat. So we think about that we have these new automated systems, or like robots. We can now send them into disaster zones that we couldn't send people into before. They can be repurposed and commandeered to support a recovery. So we can turn a vehicle into a camera, basically with 360 degrees of knowledge. We can provide real-time feedback to stop cascades if we put these into real-time systems. And we can support the human interference, which is really important. I want to end with a plug for a new journal. I am the editor-in-chief of the journal Sustainability Analytics and Modeling, which is a new journal from IFORS. So hopefully you're all familiar with IFORS. It's the International Federation of Operational Research Societies with, I believe, 50 different societies from around the world. And it's published by Elsevier, and I hope you know about it. But basically, the idea is to use OR and analytics to take on the world's pressing challenges that range from healthcare and peace and justice and equity to power and the environment and health and so on. And so I encourage you to take a look at this journal and think about submitting to the journal. It's ours as an OR society, as an OR community, and this is our journal. This work that I've described is, a lot of different things and had a lot of different people involved over many years. So I want to give a shout out to all of them and state how wonderful it's been to work with all of them. And last, just some thoughts about equity. I don't want to go into this slide, and I'm sure I'm over time, but I want to share some thoughts. When we are in disaster situations, there are undercurrents of things that we don't account for. There are things, sort of behind the scene that are, I don't know the right word for this, but it's like endemic to our decision making. And so we often don't consider that the actions we're taking or the response things we're preparing for may help one part of the population and not another. And I think it's really important for us to start putting that on our radars as we think about these disaster situations. There's a lot in this area. Sorry, I don't know why I stole that from something else I'm going to give, and I had my voice on it, so I'm sorry. So this slide is just showing the publications we have in this area, which are a bunch, and how to reach me. So I am at George Mason University again, and very happy to get to present to you all and to interact with you all. And I hope, welcome you to email me and connect after this. So thank you so much for having me.
Thank you, Alice. We have, I think that chat you can check. It is from Professor V from Taiwan. Yeah. And he said, thank you, Professor Miller, for the interesting and useful talk. I'm just waiting for the questions from the YouTube Live. By the time it comes, let me say thank you for talk on transportation system resilience. And in fact, you have covered transportation mode in almost all the areas, starting from port, aviation, healthcare. Now, I think only part left is petroleum industry.
I haven't touched that. But actually, that's interesting. In the Arctic,
I was just waiting for petroleum something transportation to come into the slide. But it was wonderful, and there are no questions on YouTube Live. So okay. I formally thank delegates who are on Zoom platform, and most of the delegates were asked to join only on YouTube Live. Here we have Professor V, Professor Suniti Hada, then Samar Singh, and many more. So thank you very much. It seems that almost everybody. Do you have any question, Professor V? Please unmute yourself. Please unmute yourself.
I think it's a very interesting talk. I'm thinking of resilience you have in many areas about the security, internet security. What should we do in terms of resilience in internet security?
So the cyber attack is what you're worried about?
Cyber security.
Yeah. So in the work that we just finished on cyber attacks on hospitals and resilience of that, one of the things we were considering was when to pay should we pay that ransom and get a little reduction in the time that it takes to start getting prepared again. So start repairing from the system versus just doing it in-house if I have the capabilities, which would require that I have some good backups and maybe off-site, duplication of my system. And then there's also the ability to sort of twin your system through the cloud. So I'm no cyber expert, but this is what I'm learning from working with folks who do this. So that ability to twin your system would also help you to then flip your system out of where you are when you're attacked and get off of that part and use the twin of it. These things are expensive to do, of course, and sort of those cloud backups are not cheap. So I guess the question is how much to invest in this. And of course, anyone in the cybersecurity area will tell you. My brother's in there, and some of my other family members work in this area. And they'll tell you that not enough is being done to prevent the cyber attack, that there are a lot of things that can be done that are just not implemented. So I think I'm no expert in this area, and I don't want to say too much about it, but I do think this is a really, really important big area that we need to really be thinking about, and that ransomware attacks are seemingly on the rise. And
Thank you very much.
I think one other thing I just want to mention about that is just that the attacks are on everything. Our whole society is built on infrastructure that has cyber built into it now. And so we're now really vulnerable. And so I think it does require a lot more attention. Thank you.
Thank you.
Okay. Elise, we have one more question from the delegate, Prabjot Kaur. What are the basic papers that refer in this topic?
In general, there's so many papers out there now. So when we started, there were almost none. And I think maybe, I can count them on my hands. And now there's probably 1,000 out there of different papers, maybe more, I don't even know. I can tell you let me go back to my slide and here that our very first paper is this number 2 paper where we were only thinking about resilience and the taking action after. And then the other main paper we have is, I think, number 3. Number 3 is where we brought that preparedness stage in. And those are pretty basic. In terms of my papers, the 2 that make it really easy to understand are number 1, where it has that port application, because you can really see it applied to something, and that airport one. This number 5, number 5, because both of them have these very clear case studies with, what comes out of it. So I think those are good papers to start with. And then there's many other people who have worked in this area. I wouldn't attempt to try to pick between them at this point on the fly. Thank you.
Any other question from the Zoom platform delegates? On YouTube, we don't have any query. Yeah, one more is there from Sumita Nathan. What type of research can be done on EVs? Sumita, you can
ask
mute
directly.
yourself and ask.
Yeah. Ma'am, that world is going electric now. There are electric vehicles which are coming up. So how can resilience be used in that area? What kind of research can be done in electric vehicles? That is something people are looking forward to.
So I think the first thing is we have to think about what's the system, what's the objective of that system, right? What performance function are we looking at? Unclear to me what we're talking about when we talk about the resilience of the EVs, and why necessarily EVs, just the electric vehicles, not the automated vehicles, but just electric vehicles. I can't tell you that I've really thought too much about this. I'm not sure what we'd be looking at. So we could be looking at individual vehicles and the system of the vehicle itself, and making sure that it's resilient to an attack, like a cyber attack, a ransomware attack. That for me as a user of the cars, I would hope that we can make sure that.
As far as infrastructure is concerned.
I see. I don't know. I haven't thought about it. I'm just thinking on the fly here, so I don't want to just dig myself in further because I'm not coming up with too many good ideas right at the moment. I haven't worked on that, but I'm sure that there. So let me just say this. So when we take on a new area that hasn't really been studied, we have to really think about what do we want to look at. So I'm right now working on resilience related to the Arctic, and I really didn't know where to start. What does it mean? And so I look up what the Arctic Council is talking about. They're talking about social and ecological resilience. And I'm thinking, it's a climate change. This is like long term and it's sort of vague. And I'm like, what can I contribute to that? Probably nothing. But what can I look at is a very specific community. And I can say, how resilient is that community to the increased changes from climate change, like upon a thawing permafrost that's underneath the infrastructure and melting. So their actual infrastructure the foundations are slipping out from under them. How resilient is that society, that particular community? And when I did that, I can see how I can contribute. So I feel like when you get these big overarching questions, it's like, what do I do? As OR people, we make decisions. So we need to think about how to give from the decision support kind of perspective, where if we're talking about this general social ecological resilience to all of climate change, I don't know what we can do as OR analysts. So I'd like to get down into take a bottom-up approach and look at the specific application and who are we talking about, and what does continuity of business mean in that particular, for them, and then start to ask about resilience. So I don't know if that helps, but that's what I'm learning to do.
Okay, thank you, ma'am.
So thank you, Professor Elise. On behalf of Operational Research Society of India, Ahmedabad chapter and Department of Mathematics, Gujarat University, I thank you because your vast research experience will have good number of questions, and delegates can directly write to Dr. Elise, and I think she will be happy to respond. So thank you.
Yes.
Thank you.
Thank you for having me, and I hope one day to meet you all.
Yeah.
Everyone stay well.
Once pandemic gets over, we will surely meet.
Bye. Thank you.
Bye. See you.
Bye-bye.
Thank you. Bye-bye.